In this video, let's go through an example of how to predict rovibrational spectra, or combined rotational vibrational spectra, using known properties of diatomic molecules. To be specific, we're going to go through example 6-3 in the book, and this reads that the bond length of Cn is 117 picometers and its force constant is 1,630 newtons per meter. Predict the rotation vibration spectrum of Cn. Okay, so our knowns are the force constant. So this is that K is equal to 1,630 newtons per meter, and the bond length here, which is, I'm going to say L is equal to 117 picometers. All right, and now remember the spectra that we saw before. The most important parameters that give the shape of the spectra are omega tilde and B tilde, right? Where this omega tilde comes from the vibrational problem and B tilde comes from the rotational problem. And so the trick is to try to find omega and B based only on K and L. So the first thing we can do is try to find omega. Okay, so to get there, remember that omega itself, not omega tilde, is equal to the square root of K divided by mu. And given this, then we have that omega tilde is equal to omega divided by 2 pi c. Okay, so this means that omega tilde is given by 1 over 2 pi c times the square root of K divided by mu. And from this, we already know K. This is given to us in the problem. And so we just need to figure out what mu is. And mu is determined purely by the masses of the atoms in the diatomic. And since we know the identities of the masses, we know everything we need to know to figure out mu. Okay, and mu, for these two masses of carbon and nitrogen, will be given by the mass of carbon times the mass of nitrogen divided by the mass of carbon plus the mass of nitrogen. Okay, so this m Okay, so this Mn is the mass of nitrogen. And this Mc is the mass of carbon. And if we plug values in for this, then we should see that if we start by just using atomic mass units. So mass of carbon is 12 AMU, nitrogen is 14 AMU. And then at the bottom, we can easily add them together. This is 14.0, excuse me. And so this should be 26.0 AMU in the bottom. Okay, now this expression, if you notice, there's two factors of AMU on the top and one on the bottom. And so this whole expression will give you a unit of AMU. And so if we want to be able to compare this with the force constant, which is given in newtons per meter, then we're going to need to put this AMU into units of kilograms. And so we multiply this then by the conversion factor, which is 1.661 times 10 to the minus 27 kilograms per AMU. Okay, when you do the math, you see that this is equal to 1.07 times 10 to the minus 27 kilograms. Okay, so that's everything we need to know to figure out mu. And now we have everything else that we need for omega as well. This is 1 over 2 pi times 2.998 times 10 to the 10 centimeters per second. You notice it's sometimes more useful to write this directly in terms of centimeters per second because it might skip one unit conversion later on, especially if we're trying to put this in wave numbers in the first place. Okay, and then this is times the square root of 1630 Newton per meter divided by 1.07 times 10 to the minus 27 kilograms. So let's deal with the number and the units separately. So if we look at the number first, well, this is something we can easily just throw into Mathematica or do on a calculator. And what you get from this is you'll get 2.07 times 10 to the third. And now let's see what this looks like for the units. Okay, so you have, over here you have 1 over centimeters per second. And so you should have seconds per centimeter here. And then inside the square root, on the right, units for newtons are kilograms meters per second squared. And then this will be divided by meters, and all of this divided by kilograms, and then just a square root. And so if we go through, we can cancel these kilograms, we can cancel the meters, and then notice we have a 1 over second squared in the square root, which all together will give us a 1 over seconds, and a seconds over outside the square root, and so then these two will cancel as well. So that our final result is just one over seconds, or 2070 wave numbers. So 1 over centimeters or 2070 wave numbers. Quick note in editing, this mu should actually be 1.07 times 10 to the minus 26 kilograms, but everything else works out just fine. Okay, so this gives us the vibrational piece. Now we need to figure out what this b is, or we need to figure out the rotational piece. Untilde b, so just b, no tilde, is equal to h bar squared over 2I, which is equal to h bar squared over 2 mu L squared. And from this you can already tell we know everything that we need. So we can just look at the wave number version of this, which is the whole thing divided by hc. Okay, and when you work through this and simplify it, what you should get is that b tilde is equal to h divided by 8 pi squared c times I, which expanding I is equal to h over 8 pi squared c mu L squared. You notice now that we have everything we need to figure out what b is as well. Okay, so because this really is a pretty straightforward calculation, it just requires a lot of care with the units, and we already saw how to do this up here. I'm not going to go through this step explicitly, but I will direct you to the notes if you want to see how this can be done. And I'll just tell you that the result you get out of this is 1.91 wave numbers, 1.91 centimeter inverse. Okay, so let's collect our intermediate results up at the top so we can make some room to draw a spectrum. So this is 2070 wave numbers, and then b tilde is equal to 1.91 wave numbers. Okay, now we can use this to sketch a spectrum. So the first thing we do is we draw our axis. So this will be sort of the energy axis, and the spectrum is going to be centered around omega, right? Remember, you have vibrational structure, or you have rotational structure that are spaced outwards starting from omega, and so this will be the center of our X spectrum, and so we're going to sort of center it around 2070. Okay, but remember there's no transition exactly at omega. There's only transitions at omega plus and minus 2b tilde. Okay, so 2b tilde will be 3.82 centimeters. And because I can't draw much more detailed than that, we're just going to call this 4 centimeters for the purpose of this drawing, or 4 inverse centimeters. And so then that means that over here at 2074 and over here at 2066 will be your first peaks, right? So here you'll have your first vibrational rotational peak at 2074 in the R branch, and then your first P branch is over at 2066 over here. All right, so the next line will be at omega tilde plus 4b tilde. So this will be over here, and also at minus 4b tilde, so over here. And these lines are at 2078 and at 2062. And again, these units are all wave numbers. And so on. You'd have another line with basically the same spacing going to the right and to the left of this. And these extra lines would be at 2082 approximately and 2058 approximately. So the peaks to the right, again, these are what's known as the R branch, and the peaks to the left of omega, these are called the P branch. The way that I try to keep these straight is to just remember that the R branch is to the right. When you lay this out in terms of energy, the R branch sits to the right of omega tilde, and the P branch doesn't, I guess. The actual intensities here, or the sizes of these lines, are more complicated to predict, and they include details about the dipole moment of the molecule, its temperature, and things like that we're not going to try and predict outright. But we do know where the positions line up, and there are, in principle, more and more of these going off to each side. Okay, so that is how you can predict what the rovibrational spectra looks like, just based on molecular parameters like the bond distance and the force constant. In the following lectures, we'll start talking about complications to this. So what happens when these two things interact with each other, or which end up subtly changing the structure of the spectra.